Hi everyone. Okay, we're going to pick back up with singular values and spectral decomposition. I want to just outline the process for how you would find a Q and the P matrices, which a few people had trouble with and wanted me to cover today. So we have this general setup here. It's essentially, nothing different than we've seen before. We have a really simple matrix, sigma, equal to an original matrix A that we're given, multiplied on the left and right by some change of basis matrices to get us there, right? I think it's helpful before we find Q and P to do some dimensional analysis and just see what dimension everything is. A is going to be an M by N matrix in general. And to preserve that through linear transformations, right, we need sigma itself to be M by N as well. That tells us that Q has to be N by N and P has to be, sorry, the other way. This tells us that Q has to be M by M and P has to be N by N. And so that can help us out a little bit with making sure we're on the right track with which method we're using. But essentially, to find sigma and to find Q and P, we have to work with not matrix A, but with matrix A times its transpose in some way. So we have two options. Essentially, we're going to work with A transpose, or A transpose A, and we're going to choose whichever one's smaller. So let's go ahead and look. We have if M is less than N, then I know that A transpose is smaller than A transpose A. Okay, so you can convince yourself that pretty easily. Because that tells us that A transpose A is M by N times N by M, which is an M by M matrix. And A transpose A is N by M times M by N, which is an N by N. And we showed that that is bigger than M. So we want to be working with A transpose. And so here's the deal. We're going to find sigma by finding the eigenvalues of A transpose. Take the square root of them and put them along diagonal. Okay, so sigma is the easiest one here. That shouldn't be too difficult. It's finding Q and P that are more difficult, but we're going to make use of the fact that we're working with A transpose here. We know that when we multiply a matrix by its transpose, either on the left or the right, we get a symmetric matrix. So that's the whole beauty of this thing. If we're working with a symmetric matrix, we know the eigenvectors form an orthonormal basis for that n or m dimensional space that we're working with. And that's exactly what we're trying to find. Q and P are going to be formed with orthonormal bases, so we're going to use the eigenvectors of A transpose because it's symmetric and it will give us the ones we need. Okay, so to find Q, we're going to find the eigenvectors of A transpose. And you might be wondering, why are we filling Q with the eigenvectors? Why not P? Well, let's look at the dimension. A transpose, which is the one we're working with, is an M by N matrix. So its eigenvectors are going to be M by 1, right? I can't put an M by 1 matrix, an M by 1 vector as a column in an N by N matrix P, right? I need to put it in Q because Q is the right dimension. So Q again is an M by M matrix, so it can fit my eigenvectors. And then what I'm going to do is I'm going to normalize them one by one. And if I need to, I'll use the Gram-Schmidt procedure to make sure that they're orthogonal. That only pops up when you have eigenvalues of higher multiplicity than 1, but be cautious that you might have to use Gram-Schmidt pretty simply to find the normalized versions of all your eigenvectors. I'll put if necessary here. Great, so that's Q. P is a bit more difficult to find, but I'll just tell you the procedure. This is in the notes. You're going to find the column vectors of Q transpose A. Okay, so these vectors, Q transpose is M by M, right? A is M by N. And so my remaining vector, sorry, this matrix here is going to be M by N. So its column vectors are N by 1 vectors. Okay, so I know I can fill them. I can use them to fill P because P is N by N, which is exactly what we need. And we're essentially going to trust the fact that we're working with a really nice matrix that's symmetric, that this will give us the vectors we need. Okay, so we're going to get these vectors, we're going to normalize them. And we're going to note that they're orthogonal. It's really interesting, actually, that the vectors you pop out here in this matrix are going to be orthogonal to each other. But you might not have enough of them. So in the example in the notes, in fact, you needed 3 of them, but you only got 2. So you went looking for that third one in the null space of A. So this one was fairly well documented in the notes, but it gets a bit confusing when you start working with the different matrix. In particular, if we decide to work with A transpose A instead, the process gets flipped a bit, okay? So I hope this was clear on how you find sigma, Q, and P. It's important to note that you're putting these vectors here, the eigenvectors of AA transpose, into Q itself, and then you're taking the transpose. These are not going to form the columns of Q transpose, they're going to form the columns of Q, and then when you take the transpose, they actually end up being the rows of Q transpose, okay? In case that was confusing, just, stick with the documentation. All right, so the next option then, if M is actually greater than N, then we know that A transpose A is smaller than A transpose. So we have A transpose A is going to be N by M by M by N, which is N by N. This is going to be an M by M matrix, as we just saw, and we know that N by N will be smaller. Okay, the process changes a bit here, but for sigma, we're doing nothing different. We're finding the eigenvalues of A transpose A, we're taking the square root, and we're putting them along the diagonal. Okay, that's simple, not too bad here. Now finding P and Q. In particular, let's look at the dimensions again. If A transpose A is an N by N matrix, then its eigenvectors are going to be N by 1. Okay, so I need to use the eigenvectors to fill my matrix that has the dimension N in it. But now this formula up here still applies. So I need to use my eigenvectors to fill P this time, because they're the right dimension. So P, I'm going to use my eigenvectors of A transpose A. Remember, P is N by N, and these are N by 1, as columns in P. Before I do that, though, I need to normalize them. And again, I need to use Gram-Schmidt if necessary, meaning if I have multiplicities of eigenvalues that are greater than 1. Okay, so that's the main difference here. And then Q is M by M. So I'm going to find the column vectors of A times P. So the matrix I just found. Let's do some analysis on here. A is N by M. Sorry, wrong way. A is M by N. P is N by N. So my matrix here will give me an M by N matrix. And so the columns will be M by 1, which is exactly what I need. I need to normalize these, and I need to use them as columns in Q. And again, like in the notes, you might not have enough. So if more needed, where am I going to go looking? Well, I can't go looking in the null space of A. Let's look why. The null space of A are all the vectors that get sent to 0 under A, right? So A is m by n. If I need to multiply a vector, it's n by 1 to get me an m by 1 matrix. These right here is my null space of A. They're going to be n by 1 column vectors. And that can't happen, right? I need m by 1 vectors. Simple solution, we're going to look in the null space of A transpose. So again, this is going to be n by m. So my null space then will be m by 1. Right? Those are the vectors I can multiply by A transpose, and those could possibly be sent to 0. So you're going to be looking in the null space of A transpose. And to make this explicitly clear, I'm going to get rid of that. Okay, so I know it's very complicated. I found the easiest way to go through this is to making sure your sizes are matching up. So you're making a choice originally if you're going to be using A transpose A or A transpose, and based off of that, your eigenvectors are going to be one particular size, so you have to use them to fill the matrix of the corresponding size. And then you have to make sure that the other matrix that you're filling, you're using the right matrix multiplication here and here to get the right size vectors that are going to be orthogonal to each other already. Okay, so I hope this was helpful to outline the process a bit more. We don't have time to do an example, but there are plenty in the notes